Row, row, row your boat gently down the stream. Merrily, 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 life is but a dream. Yep, no budget for theme song, so that is it. My name is Ohan, and this is Apes and Drapes. This episode is brought to you by paint. Yes, paint. Not only is it useful for manipulating the wavelengths of light that are reflected by a surface, but also incredibly handy for use in metaphors. It's paint, the visible spectrum of light represented in liquid form. Alright, here we go. Imagine that 100 marbles are dipped in red paint and then dropped from the ceiling all at once onto a solid white floor. As the marbles roll around, expanding outwards, you can see exactly where all of the marbles have been. They create a web on the floor in red paint. The outline of that web is the entirety of space. It took time for everything to roll from a single location, which is clear even if you walk in after they've been dropped. This gives us a loose analogy for energy and matter, which includes light, and of course gives us notions of space and the passage of time. But here's where some relativity comes in, which is how space and time are linked. Imagine that because you loved coloring so much, I asked you to fill in every red line that the marbles made along their path with the color blue. The only thing is that the closer you get to a marble, the more perfect I want your coloring to be, meaning less straying from the lines and less red peeking through the blue. Now, if I recorded a video of you coloring every red line blue, with your permission of course, though you'd really enjoy coloring so much that time just flew by for you regardless, what I'd see on the video was that as you got closer to every marble, you ended up slowing down more and more because you're spending more and more time with each centimeter of line. Of course, you'd only spend time within the web that the marbles have created because outside of the web of paint, there's no paint for you to repaint. It's not even in consideration. In this analogy, the marbles and the paint are the matter and the energy in the universe. Though it's clear there's a lot of other stuff present as well, which is represented by all the unpainted parts of the floor that are within the outline of the web. Similarly, there are a lot of things in our universe, poorly named dark matter and dark energy simply because they don't emit light, that we can't see but know is there, kind of like how all the unpainted floor within the web that the marbles have made still exists, but just has no color. The fact that you'll be moving slower the closer you get to a marble is part of the theory of gravitational time dilation, which is part of Einstein's theory of general relativity. It states that the greater the gravity, the greater the time dilation, meaning the flow of time slows as you approach a massive object. This is one of the ways in which space and time are linked, and also the ways in which they are relative. Your distance from the marbles determines your speed, but whether you're the one coloring or the one observing the coloring is what will determine your experience of the time. Okay. So the problem with an analogy is that it usually ignores some things. The main thing we're ignoring here is geometry. The most common geometry, which is just called geometry, is Euclidean geometry. This is what we're all given in school. But there are actually more varieties of geometry. How can there be more types of geometry? Well, when Euclid gathered everything known at the time about geometry 2,300 years ago, he put forward 5 axioms, meaning core assumptions that act like rules, on which all Euclidean geometry is based. The first 4 axioms are standards in every geometry. But if you play with that 5th axiom, you can start to do some really interesting things. The 2 main types of non-Euclidean geometry are elliptic geometry and hyperbolic geometry. They basically play with the curvature of the space that Euclid's first 4 axioms can be applied on by altering the 5th axiom. The 2 major names in these 2 fields are Riemann, who worked with elliptic geometry, and Lobachevsky, who worked with hyperbolic geometry. It was Riemann's geometry that Einstein used to build out his theory of general relativity because it allowed him to have the mathematics to consider a space in a way that Euclidean geometry just doesn't allow. The calculation of these geometries requires calculus, the invention of which changed the course of history. The purpose of calculus is actually quite simple to understand given how profound the idea is, yet most of the people I speak to, even those who've taken calculus, don't know how calculus was invented or what it's even used for. Well, calculus is the mathematics of calculating the continuous change of a line or shape by breaking it into infinitely many infinitely small pieces called infinitesimals. What does that mean? Well, imagine dipping a ball in paint and giving it one big push diagonally upwards on a hill. Unless you've got triceps like Zeus, who love this sort of thing, it's not going to get to the top. Instead, it's going to roll diagonally up for a bit, then round off and start rolling diagonally down away from you. How would you calculate the path of the trail of paint that the ball makes as it is rolling? That's where calculus comes in. Calculus has 2 major concepts, derivative and integral, which is where we get the names for its 2 branches, differential calculus and integral calculus. Now, watch the simple magic. I predict that by the end of the next sentence, which will be shorter than this one, you're going to understand what each of those two branches are concerned with. A derivative is the slope of a curve, and an integral is the area beneath a curve. It's that simple. Differential calculus is about finding the derivative of a function, which means essentially the rate of change of a curved line. Rate of change meaning how much the curve bends or doesn't bend as you follow it along. And integral calculus is about finding the area beneath a curve by breaking the inner part of the curve into infinitely many, infinitely small pieces. They are, of course, very closely related, and in some ways are the inverse of one another, though they require different maths to calculate. We can imagine these ideas pretty easily. We all know what a curve is. But discovering the equations was a very difficult task, and many had tried and come up with good estimates for 2,000 years before Isaac Newton and Gottfried Leibniz, amazingly during the same decades, separately developed different parts of calculus, with each of the men at different times claiming the other had plagiarized them. This actually caused a big rift between English mathematicians, which Newton was, and the German ones, which Leibniz was, for about 100 years. Now, as a side note, it's important to know that this is not simply the maths of calculating the overall slope of a curve, which had been discovered a long time before that. Calculus looks at the slope of a curve at any point in the curve, which requires you to calculate the slope of a line tangent to the curve to figure out its rate of change. If I lost you at that last part, don't worry. The fact that you can understand that it helps calculate a curved line as the line is in the act of curving is the most important part. That's why it's called the mathematics of change. What is the big deal about curves? Well, much of our reality can be broken down into curves. Things like volume, surface area, trajectories, and orbits. The list is endless because nothing is really even or perfectly straight. Nature has much less of a fascination with hard corners than we do. If you're familiar with fractals, a fractal zoom is basically a visualization of the idea of an infinitesimal. That's what calculus is doing to a curve to calculate how it changes. So, these two mathematicians had different aims. Leibniz was more interested in graphs, rates of change, and more of the pure maths applications of calculus, whereas Newton was more interested in physics and astronomy. Newton is famous for consolidating ideas about the movements of planets and coming up with a coherent theory of gravity, which was a big improvement on our previous ideas, which seem silly to us now, like Aristotle's theory, which said that everything has a natural place that it moves toward, meaning that when an apple drops from a tree, it's because that apple had wanted, since before it sprouted from the branch, to fall to the ground. It's more complicated than that, but we have the theory of gravity now, so I'm not going to go into it. But back to Isaac Newton, who is looking up at the night sky and going through all of the work of everyone that came before him. Really important figures like Copernicus, Galileo, Descartes, and Kepler. Amazingly, the last three were alive at the same time, the mid-1500s to the mid-1600s, which, as a side note, is also when Shakespeare was alive. Crazy time. This is all 100 years after Copernicus birthed a massive change in the European scientific community, effectively beginning the European Age of Enlightenment, and one could argue that Copernicus paved the way for the others to exist as they did. So Newton, in the mid-1600s, is looking at the night sky thinking, how the hell is all of this working? And then he does something amazing. The reason why he's one of the best known names in history. He combines all these complex ideas and comes up with a beautifully simple mathematical explanation for not only why we can walk on Earth and apples fall from trees, but also why planets revolve around the sun and how comets fly around the solar system. This, of course, being the theory of gravity. In addition to this, he also calculates the motions of objects when gravity is acting on them, meaning the orbits of planets and the trajectories of things thrown in the air. This lets us calculate things like how fast something thrown into the air would have to go to get into space and land into orbit, and also what the moon's orbit looks like when the moon is revolving around the Earth, while the Earth orbits around the sun. There are really endless amounts of objects, patterns, trajectories, shapes, and the relationships between all of them that gravity and the maths involved allow us to calculate to better understand. That's why calculus is fun. That's why it's important. And that's also why understanding what calculus is and what it's used for isn't something to be confused about. It's all accessible if we take the time to understand the context behind the information and the contrast of what we've gained from it. Interestingly for us, now in the middle of the COVID-19 outbreak in March of 2020, Newton made these discoveries between 1664 and 1666 when there was a plague in London and he was in a precautionary self-imposed quarantine, which, by the way, was when he was only in his mid-20s. The funny thing is, he just solved it for himself to help him with the theory of gravitation because it was bothering him. It wasn't until he and Edmund Halley, who was working on planetary motions, were sitting in a bar in 1684, and Halley complained about his trouble trying to figure out orbits that Newton was just like, oh, that? Yeah, I figured it out 20 years ago. No big deal. You can have it. And of course, this blows Haley's mind, who then pretty much single-handedly funds the publication of Principia Mathematica so the rest of the world can learn about gravity. By the way, Haley is the one who figured out that comets, like Haley's comet which bears his name, the ones that we'd been observing in some cases for thousands of years, were the same ones that were just continually flying around the solar system. As another small tangent, the guy who told Haley to go visit Newton was Haley's mentor Robert Hooke, a great scientist in his own right, who was arguably the first European to chronicle his experience with cannabis, and his journals about it are pretty great. He's introduced to cannabis by his friend, the famous sailor Robert Knox, who had an incredibly interesting life sailing around India and Sri Lanka, and was the main inspiration for Daniel Defoe's novel Robinson Crusoe. And Daniel Defoe, aside from being a novelist, was also a pamphleteer and spy for the group supporting England's Revolution of 1688, which removed King James and installed his brother William III as king. There's more, but if I keep going, this episode's never going to finish. Infinitely many tangents, just like calculus. Why tangents? Well, I think understanding the context behind information is helpful for remembering we're better at remembering information that fits into a narrative rather than information that drifts freely through the vast space of abstract thought. Even ideas are beholden to gravity. I wrote this episode because nobody ever told me why calculus was invented. Nobody ever gave me the opportunity to try to discover calculus for myself. And though I likely wouldn't have succeeded, nobody ever gave me the chance to at least think about the theory behind the math. Even if I wasn't asked to invent the method of calculation itself, I was never introduced to the fun of the pursuit. I was never given the context behind how calculus was discovered and the contrast of why it was important to at least have an understanding of. The thing is, nobody I speak to about their education was ever given those two things. Not just with calculus, but with most of the things that most of us have been taught. We rob our children of the right to discover in order to make assessing them easier to execute. We drain the curiosity from children while paradoxically depending on them to discover on their own something they are passionate enough about to pursue. We ask every child to find a way to add value to society despite our education system's best attempt to ruin their relationship with learning. Within the first 10 years of my life, multiple teachers told my parents that I was bad at math. Within the last 10 years of my life, I built a career around my capacity to do the math others couldn't. There's so many anecdotes like mine, and they all point to the same conclusion, that we stop telling children that they are struggling with what we ask of them as students instead of admitting that we are struggling with what is being asked of us as adults. Exploration, the freedom to explore, is the most significant aspect of the human experience. The excitement of learning and the passion for curiosity are the most fundamentally human things there are. Every child deserves to have their curiosities answered with even bigger questions, because there's nothing that we've ever come across in this vast, unforgiving universe that is as precious as a child filled with wonder.